Hello everyone, I am Bhavyashri. I am from ECE department and my roll number is 24BQ1A0439. Today I am going to give a seminar about stationery process and the types of stationery process. First of all, what is a process and what are the steps included that a random process is going to be stationary. So if we consider a random process is said to be stationary, then its all statistical properties such as mean, moment, variance, etc. do not changes with the time. It means that a random process consists of various statistical properties and that statistical properties do not changes with the time. So next one is the stationary of a process can be classified into different levels or orders depending on how the probability density function behave with respect to time. It means the statement above tells us if a random process is said to be stationary, then its probability density function, it means it tells us the behavior of its probability density function with respect to time. That means how it was changing with respect to time. So there are two types of stationary processes. First one is first order stationary process and the next one is second order stationary process. First of all, what is first order stationary process? It means if a random process x of t is said to be first order stationary process, then its probability density function do not changes with time or shift in time. It means if the first order probability density function how it was changing with respect to time or how the value is shifting time. So mathematically we can conclude that fx of xi comma semicolon comma t1 which is equal to fx of xi semicolon t1 plus delta t. Delta t is nothing but the shift in time and whereas t1 is the time instance. So it means we can say that the probability density function fx of xi comma t1 is independent of the actual time instance. So it means that mean is independent of it. So therefore we can say that the mean value of the process remains constant with the time. It means, so we can say that for a first order stationary process, the mean value remains a constant at all time instance. So therefore e of x of t is equal to x bar which is equal to constant. So for first orders we can have constant mean. Here the proof is, let us consider x of t is a random process and x1 of t is a random variable and x of t2, whereas t1 and t2 are the time instances. We can take t2 is equal to t1 plus delta t. So by applying expectation for the random process, we can have e of x of t is equal to integral minus infinity to infinity x1 into fx of x1 into t1 into dx1. So next equation is e of x of t2 is equal to e of x of t plus delta t. We previously take that t2 is equal to t1 plus delta t. So by substituting the t2 value in it, we can have integral minus infinity to infinity x2 into fx of x2 into t1 plus delta t tx2. So by deriving these equations, we can have e of x of t1 plus delta t, so that is e of x of t. Here why we taken the x of t means, if the shift in values, if the shift in time, there is no change in the present equation. So we can have E of x is equal to mean, which is nothing but a constant. So for all first orders we can have constant means. Next one is second order stationary process. So previously we have taken the first order probability density function. So similarly we can have the second order probability density function, that is joint density function. So if a random process is said to be second order stationary process, that means if the joint probability density function does not changes with time or any shift in time. In simple terms, if we have the shift time axis, the joint density function of the random variables or at two time instances remains the same. So if we take two time instances like t1 and t2, we get the same value. Therefore the mathematical equation here it is fx of x1 comma x2 t1 comma t2 semicolon t1 comma t2, which is equal to fx of x1 comma x2 semicolon t1 plus delta t comma t2 plus delta t for all t1 t2 and delta t. Therefore it means the function depends only on the time difference, which is nothing but t2 minus t1, and not on the actual time instances t1 and t2. So here we can see that for every second order stationary process is also a first order stationary process. So here the statement tells us every second order stationary process is also first order stationary process. It means that if the joint probability density function obeys the first order stationary process, that means it is also obeys the first order stationary process. We can simply say that second order stationary process is also a first order stationary process, because if the joint density function does not changes with time, therefore the individual density function does not remains unchanged. So what is the condition for a process to be the second order stationary process? So for a random process to be stationary, second order stationary, then its autocorrelation function should depend only on the time difference between two time instances, but not on the absolute time. So let us consider x1 and x2 be the random variables of random process x of t at time instances t1 and t2 respectively. Therefore the autocorrelation function is given by rxx of t1 comma t2 is equal to e of x of t1 dot x of t2. So if we define tau is equal to t2 minus t1, then we can get rxx of t1 comma t1 plus tau. So final conclusion is rxx of t1 comma t1 plus tau is equal to e of x of t1 into x of t1 plus tau. Previously we took that t2 is equal to t1 plus tau. So therefore we can have the autocorrelation function. This means that autocorrelation function depends on only time differences, which is independent of the actual time. Thank you.